Okay, so now we are in part 9. I believe I said part 9 on the previous section, but the previous section was actually part 8. In any case, it is correctly labeled on the YouTube channel. What we've done so far is calculate we look at the string and the vibrations of the string, the transverse vibration of the string at the limit of the loaded string situation. So we were able to calculate everything we needed starting from the discrete equation, and then we took the limit. Okay, making sure we keep the density constant and making sure that the d, the distance between the mass, was going to 0. Now what we would like to do is to actually see what is the equation of motion that describes the the continuous string situation. So that equation is a very central equation in physics. It's called the wave equation, and we are going to derive it now. It turns out to not be very complicated. It's just a matter of remembering what the definition of derivatives are. So let's do it. Okay, so as I said, we studied the continuous string as a limit of discrete case. Now we want to write the equation of motion for the continuous problem. So, as always, we are going to start from Newton's law. Let me remind you, this is a Newton's law that we've seen earlier. We could actually get that result as well from Lagrange mechanics, but that's the equation of motion for the discrete case, where we divide left and right by d just because it's going to make our life a little bit easier in a second. So you see this equation is simply on the left-hand side the acceleration times the density, and on the right-hand side we have the forces acting on mass qj. And we have two forces, one that's due to the interaction with the left mass, which is the mass that's actually located on the left at qj minus 1, and the mass that's related to qj plus 1 on the right. So it's this difference between those forces is actually the net force on qj, and therefore the acceleration is given by Newton's law. Now we are going to go into small d limits, and actually here I already kind of did half the work for you because I put between parentheses the right form that looks very much like the difference between two consecutive qj divided by the distance. Now, if we do a very small distance at the small d limit, to d going to 0, those differences are related to the derivative of q's with respect to distance. In other words, we can see that when d goes very close to 0, we get the derivative. In this case, it's minus because of the order at which we wrote the q's. One thing I'd like to remind you is that because this equation is actually an equation coming from the right, in other words, we look at the difference between q at one position and the difference further to the right, so displaced by d. That's the reason why the vertical bar says x plus d over 2. So we're actually calculating the derivative in between those 2 points, x and x plus d. Therefore, it's the derivative x plus d over half. Okay, that's going to become important in a second. The second expression in the parentheses is similarly, actually the first one, this one was the second one. The first one is similarly obtained from derivative on the left. And so for itself as well, we find that the equation gives me the minus the derivative of q with respect to x at x minus d over half. And again, as I reminded you in the previous part of the previous screencast, we have partial derivative because we now know that q depends on both x and t. So we have two variables. When we have multiple variables, we use partial derivatives as it is customary. Now there is one more thing we need to do, is that it turns out that the right-hand side is the difference now between two derivatives divided by d. In other words, is going to be another derivative, the derivative of the derivative. And this is how we are going to see the second derivative. In fact, it's better to do it by writing it. We see that the right-hand side is going to be the derivative of the derivative. In other words, it's going to be the second derivative. And we kept the tension on in the string in front of the parentheses. So we can drop the vertical bar at x when we calculate something at the position itself. So that's no problem for the last equality. But we did a big job there. We already expressed the right-hand side as a second derivative of q with respect to x squared. So we are almost done. Not quite, but almost done. So let's finish what we need to do. Now we are going to take the limit d equals 0 at this equation. So we actually saw that what we obtain in that case is this very important equation, that the right-hand side is tau times the second derivative of q with respect to x, so the second derivative. And the left-hand side, we did one more thing. We actually wrote that the mass per distance is the density, or the linear density in this case. And if I write the q dot dot explicitly as the partial derivative of q with respect to time and rearrange the term, I obtain this extremely important equation in the red box, which is the wave equation in one dimension. So that's actually the differential equation we would have needed to solve if we wanted to find the value of q using a more direct method instead of using the limiting the methods that we use of a loaded string for which we look at the continuous limit. So we can also, this is a very important equation. I'm going to rederive it now without using the discrete case at all. I mean, that's useful to do because we want to make sure that we're in good shape, and it's such an important equation that we want to make sure that we understand what's going on. So for that, we're not going to start from the discrete case at all. We're going to start with the continuous case, and we are going to consider a very small element of the string of length ds. And that length ds extend between x and x plus dx. So the horizontal distance is dx. So this is one of the other opportunity for you to pause the screencast and making sure that you understand this plot very well. The reason why there is a deformation in the deformation dq in that small segment of string is because you have tension in the rope in the string, both on the right and on the left. As we said from the beginning, we suppose that the tension is of constant magnitude. However, it is not of constant direction. That's the reason why you have a deformation. So let's try to now that we have all this information, let's try to derive the equation that we want to. So before that, let me remind you a bit how we set up the problem. So we have a segment of length ds, and it's fixed at both ends far away, right, at the very x equals 0 and x equals L. We imagine that the dq is a displacement from equilibrium, so the q describes the equilibrium. As I mentioned, the magnitude of the tension is unchanged, but its direction does change. The length of the string will be described by sx of t. So s is really, if you look at the picture, the element ds is the actual length, right? Is along the bold line, the line in heavy markings. The density is constant, of course, it's nothing new. We are going only to consider small displacement, dq, of course, it's fine. We are going to consider them small, so we are still well into the limit of what we discussed so far. And it's going to be perpendicular to x. So in other words, we are looking at transverse waves. So waves that deform perpendicular to the string. And the mass of this length ds is obviously rho ds, rho being the mass per distance. So if the distance is ds, the mass is rho ds. And what we are going to do now is to write the Newton's law for that particular element of the rope, of the string, and we are going to look at the force on that string. So there are two forces that will actually act on that segment, and the two forces will be the tension on the left and then tension on the right. And of course, because we are looking at displacement in the vertical axis, the dq, which is the y-axis as well in this case, we are only going to be interested in the projection of the tau, of the vector tau on the left, on the right, on the vertical axis. Okay, I think that we have everything that we need now in that text. And let me translate that text into math, and then we should get the right equation. So first of all, let's write Newton's law. The net force, delta F, is going to be equal to the mass times the acceleration. So that's simply rho ds for the mass, and the acceleration is the second derivative of the displacement with respect to time. So that shouldn't be a big surprise now. Now, the difference in tension is a little bit more subtle to do, so let's do it carefully. The difference in tension is actually obtained by this equation. Let me explain to you. The way we define the theta 1 and theta 2 on the figure, we see that the force on the left is going to the left, right? Is a negative force. So it's minus tau times sine theta 1. And the reason why it's sine theta 1 is because it's the projection on the vertical. So we are looking at the projection on the vertical for the component of the force that's vertical, since it's the motion that we're interested in. And likewise, on the right-hand side, the contribution to the right, so the contribution that pulls the string on the right-hand side is theta sine theta 2, and it's a plus sign because it goes to the right. So I think that's pretty cool. Now, what we can do, we do the usual trick, is that when we have pictures like this, very often the first thing we do, we say that because we have infinitesimally small displacement, which is of course the case here on an infinitesimally small segment, the sine and the tangent are the same. Are the same, exactly the same at the limit of infinitesimally small dx. So we do this. Now, what's nice about the tangent, of course, a tangent of a segment is nothing else than the slope of that tangent. So this is from a straight line, and that slope is given by the derivative of the function as a function of the variable, in this case x. So tangent theta 1 will be the derivative of q with respect to x, calculated on the left-hand side, so at x, and the tangent theta 2 will be also the derivative of q with respect to x, but calculated on the other side of the string, so at x plus dx. So we obtain directly these equations. And once again here, if we were to divide that expression by dx, we would see directly the definition of the derivative of dq over dx. In other words, the second derivative of q with respect to x. So that's why we obtain this result. And I would like to also attract your attention. The tau is there in the way, but it's never involved in anything. It's just multiplied all the way. And the dx that I added there on the right-hand side of the last equation is simply because I had to divide by dx the previous expression in order to calculate the second derivative. So now the force in the vertical direction will be equal to mass times the acceleration in the vertical direction, and again vertical because we look at transverse waves, and therefore the two expressions I have are the same, and so we can write what the result in the blue box. One last thing that we had to do as well is to say that ds is almost equal to dx, which again for a very, very small dx is exactly the case when we have an infinitesimally small string. So that's very nice, because now we were able to calculate the wave equation in two different ways, and we do not necessarily learn more with this expression other than the fact that we were able to manipulate one more time the different variables that we have to work with. So it's a very good peace of mind for students to be able to understand this slide as well, because it really shows that you have a good command of the different variable and different formalisms we are looking at. So I'm going to stop this screencast here, and we are going to be ready for the next screencast, which will be about solving these equations. Thank you very much for your attention.